All right, let's begin. All right, so this is for the test one review, and the test will be as stated before. It's a very straightforward test. 25 multiple choice. You will have one conversion, one vector addition, where you give both the equilibrant and resultant in polar and component, just a standard straight up vector addition. One of the vectors will be instant conversion, the other one will be just a simple vector where the reference angle is either 30, 45, or 60. You will have a 2D motion. And then you will have a Atwood's machine. So it is pretty much the standard, a standard test. There are no tricks. There's nothing extra complex. It's just the brute force. Do you know how to do these basic problems, and do you have a basic understanding of these types of problems? So, what I've also done is on the website, or on Blackboard, I posted another test. Was it the one that we did over the summer? Was that the one that I gave you? Okay. Oh well, then I didn't. I gave you something else. I wanted to give you something else, but the Summer 213 test is good enough. It gives you a wide selection of multiple choice. On trying to think of what I need to say. The one that's on Blackboard, in the first one, it says test one pack. In it, towards the back, there's a list of another set of multiple choice. Now the matching will not be in there. The matching has changed. It's effectively become the equation sheet. And then in here, there's a list of some more multiple choice that you can take a look at that may or may not be on the test. There's a whole bunch of like sample problems and all sorts of stuff, but it generally revolves around the same thing: conversion, vector addition, 2D motion, Atwood's machine. That's it. That's all that's on the test. So what I'm willing to do is just, we've talked about it a lot on the review session on Tuesday, and so now I can I'm in a position where I can just do anything that you guys want me to do. Now obviously if you ask what's on the test, or can you do a problem that's on the test, I won't do that. But what I will do is, you give me a problem, I'll do it, we'll talk through it, and for the next hour 15 minutes, we'll do all sorts of stuff. So, who has the first question? Yes?
Can you do a 2D motion problem?
2D motion problem, okay. Now with the 2D motion problem, before I even write the problem down, let's just go over what I expect on a 2D motion problem. While you're reading the problem and you figured stuff out, one is set an origin. You basically I tend to pick lower left as the origin. 2, set your positive and negative axes And do it in a way that's the standard: left negative, right positive, up positive, down negative. And 3, and this is where, if you see 2D motion and it doesn't involve the max height, if I don't say max height, you immediately throw out these equations: x equals x naught plus v naught xt, and y equals y naught plus v naught yt plus 1/2 at squared. And a is the gravity, and it's -10 meters per second squared. You write those two out, and what we're looking for is you need to ID your knowns and your unknowns. I don't know about the punctuation. This is physics, not English. So the unknowns and unknowns, and typically how I do it is I underline a unknown with red and a known with green. And it may not show up on the overhead, but it should work out well. Now let's do a problem. It will have to be non-quadratic. Yes?
What did you say number 3 was?
Say that.
Like, what did you say step number 3 was?
Oh, step number 3 is just write out these equations. Now, thinking ahead about the test. The test technically is an hour long. Like I've written it so it would take a normal student about an hour to do it. In reality, you're going to get an hour 15. The last thing you ever want to do is encourage me to give you a take-home test, because that changes the parameters of the test. With an hour-long test, I'm confined to give you legitimate problems that can fit within that time frame. So all of these problems are going to be hitting the major areas. It won't be like, give me the 15 following bits of information concerning this one problem. It has to be the high notes. Like, in terms of, let's see, what could I do? Like a 2D motion, I have a theta, which I'll give you as 30 degrees. The time that it takes for it to land is 15 seconds. And what I want to know is, what is this distance x if that height is 50 meters? And what is the initial velocity? So I've given you enough so that you can solve for it. First step, set the origin. I set the lower left-hand portion as the origin. That means that x naught is 0. That means that y final is 0 as well. Y naught is initially 50. And I rewrite this as x equals v naught cosine theta t, and 0 equals y naught plus v naught sine theta t plus 1/2 a t squared. I know what my time is, so everything with time is green. I know we're on the planet Earth, so that's A. I know that my theta is given. And let's see, and my y naught is given. That leaves me with x and v naught as my unknowns. So number 4 is, or ID your knowns and unknowns, which makes 5. Determine if it's one equation has only one unknown, or two, it's a two equation, two unknown. And when we look at these equations, the one on the left, x and v naught are both zero, or unknown, excuse me, which makes that, you can't really use that equation just yet. The other one, everything is known except for v naught, which makes this the one equation, one unknown, and which makes this the equation that you go after. So y naught v naught sine theta t plus 1/2 at squared is equal to 0. Now I have to solve for v naught. Negative v naught sine theta t equals y naught plus 1/2 at squared. Now I'm going to divide both sides by sine theta times t, a negative sine theta times t, which leaves me with v naught y naught plus 1/2 at squared over negative t sine theta. And now we have v naught as an expression of y naught known, a known, t known, and theta known. And okay, this will work out. Negative 15 sine 30. Because at first I'm very worried about this being very big and negative, but the denominator is negative, so it should work out. So my initial velocity is 143.3 meters per second. And that is the V naught. The other thing that we need to find out is x. With that x, we can solve it because now we know V naught. So this becomes this and you get something like this. This type of problem is what you'll be doing. Now, it's not exactly like this, but this procedure is the same. Understand the procedure, know your basic algebra and some basic trig, and you should be able to handle anything that's thrown at you. Yes?
Did you ever ask for the max height on a problem like this?
If I did, let's say I create a second part, and I say, now that you know the initial velocity, what's the height? To determine that,
You can time of flight as well.
well, that was the time of flight was the 15 seconds. When you're dealing with max height, now you've got something. I wouldn't, hold on, I have to change physics into English. It takes some time. When doing a test like this, I'd have to do one of, like if I was going to do a 2D motion thing, I would either do max height or I would do what we just did. I wouldn't do both. The only time I would do both is if I had a little bit more time, like in a final. The But a 2D motion problem could be done like, I've got 143.3 meters per second at 30 degrees, and its initial height was 50. I want to know its max height. When you hear max height, you're going to write two things. One, Vy is V naught y plus AT, and y equals y naught plus V naught yt plus 1/2 AT squared. Because it's at max height, you know one thing that's very important. The velocity in the vertical is 0 at max height. Now V naught y is V naught sine theta. Now let's look at our knowns and unknowns. I know my initial y. I know my V naught y, because that's V naught sine theta. I know V naught and theta. I know A, but I don't know y and I don't know t. Over here, I don't know t, but I do know V naught and theta and A. So for all of these things, you attack the velocity equation first in a max height situation. So minus V naught sine theta equals AT, or minus V naught sine theta divided by t, or no, A, is equal to t. So it's minus 143.3 sine 30 divided by negative 10. No, because in situations where the launch point and the landing point are the same, you could safely cut that flight time in two and get the time to max height. In this particular example, we started on a 50-meter cliff. The start point and the end point were unequal. So you have to do it the straightforward way and just power through it. And this should give you .165 seconds. That's the time that it took for it to reach max height. To find the max height itself, you plug it in here. Oh wait, let me rewrite this. I need more room. That's a mutant 7.165. So 50 plus 143.3 sine 30 times 7.165 and I get 307 meters. And so that would be a max height problem. Now, on a test, I wouldn't do both. I would just do one or the other. And if I did this, I would have to give you the initial velocity and as well as the angle. Yes?
So which one of those will give us it?
Not going to tell you. Nice try, though. In the back, and then you. Yes?
Work two equations and
Two equation, two unknown. Let's see. Okay, a good two equation, two unknown would be this. You have mass 1 as 3 kilograms. The coefficient of kinetic friction is 0.1. It's attached to an object, mass 2, which is 15 kilograms. For a 2-equation, 2 unknown problem, I would want to know, well, what is the acceleration and what is the tension in the string? And that's a classic 2-equation, 2 unknown. To do this, you have to first look at mass 1. It has tension to the right, normal force up, friction force to the left, since obviously this thing is going to go to the right and down. And then you've got force of gravity pulling down. Sum of the forces vertically is 0, which is normal force minus force of gravity. So normal force is equal to the force of gravity, which is equal to mg. Friction force, so that's part A. Part B, friction force determination, mu sub k, normal force, mu sub k, mg. So that's the friction force. Now to get the acceleration, sum of the forces in this case, x, which is m1a, is equal to tension minus friction force, or m1a t minus mu sub k mg, and m1g. Our 2 unknowns are a and t. So that's the reason why we can't really work with this equation just yet. You then move on to the second mass, m2. You have tension pulling up, force of gravity pulling down. Now on the left, on this thing, you have to pay attention to your loopy-droopy number line. The fact that left is negative and right is positive. The fact that up is negative and down is positive. Because we just took a number line and bent it. The sum of the forces in y is equal to m2a. Tension is up. In this case, it makes it negative. Force of gravity is down, which makes that positive. Which means I have m2a is equal to minus tension plus m2g. Now under normal circumstances, we would just eliminate t and then roll on to the rest of the problem with a. But in this problem, we're really asking for, well, what's a and what's t? Now you could solve this in several ways. The easiest way is to just solve one of the equations for tension. So now I've rearranged it so that tension is on the left and the rest of the equation's on the right. And then I'm going to take this t and plug it in there. And I get this. Now I have an equation with only one unknown, a. So solve for a. m1a I get this. Factor out a's and g's. And I get this. So now I have A. Now something that you need to be very, very careful with, G in this case is 10. It's because we handled the positives and negatives before, so we're only concerned about the magnitude of gravity. Whereas in ballistics problems, A is a downward acceleration, and so that's why we have that as a negative value. And we were just putting in -10 because we know it's down. Here, we know it's down, so we make what, well, in this case, down is positive. And it avoids that problem with, if G is negative and down is positive in this case, so we really should take a negative of a negative, and it gets kind of confusing. So this is why, for Atwood's machines, I always deal with magnitudes and let the force directions use reason to determine the positiveness and negativeness of it. So 10 M2 15 minus 0.1 times 3. 3 plus 15. And that gives me an acceleration of, should be close to 10 maybe? No. Minus 0.3 times 10 divided by 4.5. Oops. Hold on, did I mess this up? Oh, I definitely messed this up. These numbers are crazy. I must have missed a sign. Let's go back. Minus T plus FG. T minus friction force. M1A equals M2G minus M2A. We're going to take a look and see. Because it does look good. Wait a minute, I must be going out of my mind. Oh, I know, hold on. This isn't a 1.5, it's a 15. So the equation is right. Brings up an interesting point. Had you continued with this, and this is one of the things, the error that I made produced, always make my mistake a lesson so that you don't have to do it. So my calculator told me that the acceleration of this system was 32.7 meters per second per second. Is that believable? Is that a possible answer? What's the magnitude of gravity? What's the number? 10. So what I'm telling you is, you're attaching a mass onto an Atwood's machine, and now you expect this mass to accelerate faster than that of gravity. That doesn't make sense. That's crazy talk. If you got an answer like this, and this is what caused my brain to just seize up. In this type of problem, what do we know is going to happen? This Atwood's machine is going to go to the right and down. It's going to go in the positive direction. So you should get a positive number, like what we did. If we got a negative number, we did something horrible. The other thing is, a lot of people, they'll do the problem and they go, okay, the acceleration is 400 meters per second per second. So you're telling me it's accelerating 40 times that of Earth? 10 is the maximum that an Atwood's machine can run. It must, in this case, it must be positive and it must be less than or equal to 10. So if I do the calculations correctly this time, I get an acceleration of 8.17 meters per second squared. That is a number I believe in. That's a believable number. Now what we have to do next is find the tension. The tension is what we solved for, M2G minus M2A. Tension in this case is 15 times 10 minus 15 times 8.17. So the tension is 27.45 newtons. And so that's a good, quick, 2 equation, 2 unknown Atwood's machine problem. So, next, so your question.
Yeah, I was wondering what kind of calculator were you using because the calculator, I don't know how, I guess I'm putting it on, obviously, because I didn't write it.
So you don't know if your calculator is, what kind of you have something like this?
No, it's a calculator.
Oh, so you have a smaller version. What I would do is, with a smaller calculator, like I would take this, like let's say I did this equation, and then I would go 150 minus, and then I would tap in 8.17, 122.55. I would do the calculation in smaller chunks. With this is the calculator that I have, and I'm able to put in a lot of parentheses, and before I hit the enter key I can look at it and confirm that I'm going to get what I'm going to get. For the smaller calculators, I would do the calculation in smaller chunks.
Yeah, it's like all of the bigger problem with the, like finding acceleration equation.
Yeah?
Number is like 64.7. It's really low.
Well, okay, then you've done. Well, for something like this, what I would do is I would do what's in the parentheses, write that number down, multiply it by 10, write that down, divide it by 18. So you understand that you have to do what's in the parentheses first, and then whatever you're multiplying it by, and then whatever you're adding or subtracting it by. So you have to understand the basic rules of math in order to deal with it.
I have a question.
Yes?
Do we need to know A, B, and C, or are you gonna get it?
A, B, and C?
Yeah, like what was that?
The normal force and the friction force.
You need to be able to solve that on your own.
Can we do an example solving for the normal force with the problem like this?
Well, we just did the normal force. If I wanted the number for the normal force, we did it right here. With a standard Atwood's machine problem, the normal force will just be that mass on the table times gravity. But I like to do all of these steps because there may be that one problem where there is an external force being applied onto the block at an angle, and the normal force would change. Yes?
Okay, I gave my problem for acceleration just like you, but I got 9.79. Like, how much do you count off for, like, if
You got 9 point what?
79?
You're really off. You used these numbers and got 9.7. Hold on, now you're making me doubt myself. Probably had you done all of this up through here and got the wrong answer, what that would count as a mathematical error, which would be typically, depending on the mood of the grader, it would either be a 2-point deduction or a 3-point deduction on a 15-point problem. So it's not a big deal, but it's just enough to make you remember you need to be careful. Yes?
How did you, the ABC thing you was just saying, as you drive, the normal force equals FG.
Okay. For an object just lying down on the surface, you have to identify the two forces. Normal force up, force of gravity down. That's all you got. Now, if I was pushing down on the block or lifting up on the block, there would be a third force. But the tension, don't consider it as a third force in terms of vertical, because the tension is all horizontal. You know that the sum of the forces in the vertical is 0. Why do you know this? Because the object isn't moving up or down. It's only moving from side to side. Your upward force is the normal force. Your downward force is the force of gravity. So now solve for normal force. Force of gravity is the normal force, so mg is the normal force. So that's the derivation that I want you to do over and over again, because there will be that one time where I put an external force on one of the masses and change things a bit. So, yes?
So say there was a force added to one of the masses, like what part would change?
What part would change would be the normal force. Things would start getting weird. I let you know this, the Atwood's machine doesn't have an external force on it. It's only the gravity and the mass hanging off the end. Because we've kind of done problems like that in problem set 3, but we've never done an external force on an Atwood's machine problem. I can tell, I'll tell you this much, there's not one on it. So let's,
So you don't have to go.
yeah, I'm saying it, or I'm giving you that answer because this could just fall down the rabbit's hole in all the different permutations. It's a very, when you look at this test, you're going to go, taught us that, taught us that, taught us that, taught us that. No, the person who says I never taught you this, I'll be very, we will have words, so to speak. So, all right, next question. Yes?
This is just a multiple choice one, but it was the velocity vector when the ball is at the highest point.
Mm-hmm.
I know, like, the y should be 0. It was on the,
Was it on the
maybe
June?
it was on the summer routine. Not plastic.
Hold on, can you show me?
I
Or
just-
you don't have it written?
No.
You don't have a copy?
It was like 2x at something, and I think the answer was something at 270.
So appropriate velocity vectors.
The acceleration at the highest point, is that the one you're talking about?
Yeah. At the highest point in the curve, it has a velocity vector which looks like this, which means that the velocity vector has to be something that is at 0 degrees. It could be 180 if it's going to the left. Its component vector is all x. So if you have a velocity vector which is 90 or 270 or anything in the positive or negative y, that's not an appropriate velocity vector for an object at the top of the curve. In terms of its acceleration, it's pointed down. So the acceleration vector has to be at 270 and has to be at negative y direction. So the velocity vector at the top of the curve cannot be 90 or 270 or positive negative y. The acceleration vector is at 270 or at negative y. And so that kind of explains things. Yes, in the peach, yes.
There's a multiple choice question that says in an Atwood's machine the masses accelerate and then there's options.
Yeah.
Would it be they accelerate at the same rate?
Yes, They accelerate at the same rate. In a situation where you have Atwood's machines, or an Atwood machine, they're attached by a piece of string. And that string is taut. If they accelerate at different rates, the string will break or bunch up. And in Atwood's machines, it doesn't do that. So they accelerate at the same rate.
But the one, there's also one that says but different velocities, that's not the.
No, they both have the same, because they have the same acceleration, they have to have the same velocity, because if they have different velocities, it'll bunch up or snap.
Okay.
And for just as a reminder for those, I'm going to send out an email, but if anyone listening, just as a reminder, the official test is 2:30 in Brevard. However, I have the reservation for the JAC all day. And so at 10 a.m. or at noon, you're welcome to show up and take the test then. If you are an SDS student, remind me at the test that you are one, and so we'll put you, what we're going to do is we're going to separate the SDS students. They'll be on one side of the room, and the normal students will be on the other, and then we'll act accordingly. But that's just an announcement. You had a question.
Yeah, there's not going to be the sliding box problem on there, is there?
No, there isn't enough time. Really, the Atwood's machine is the culmination of problem set 3. So I have to hit the high notes. I only have an hour to do it. With conversions, add vectors, 2D motion, that's a full slate of stuff. If I did do an inclined plane with a sliding box, that could be at the final. There's a potential way of doing it on test 2, but that's for the future. I would focus on what I've said. The inclined plane will not be on it. However, the theoretical stuff behind it, like mg sine theta, mg cosine theta, how does the normal force look with respect to the surface and stuff like that, things like that are in the multiple choice. Sure. I would say to keep it simple and be able to identify, you have a box, it's on an inclined plane of angle theta. Gravity doesn't care about the way it's always straight down. The normal force is always perpendicular to the surface. These boxes typically go downhill. And then up the hill is the friction force. Friction force is always parallel to the surface. Normal force is always perpendicular to the surface. That's what it does. And then the only other two that you have left is FGY and FGX. The X component and the Y component of the force of gravity on the box with respect to the surface. Now that angle and that angle are the same. FGY is the adjacent side, so this is FG cos theta. FGX is the opposite side, so this is FG sine theta. And so just be able to label all the parts and know that that's perpendicular, that's parallel, that's straight down. These are either perpendicular or parallel to the surface. Like as if I gave you a sketch and said fill in the blanks, you'd be able to identify it. Yes?
I thought FGY was sine theta.
No, it's because your trig teacher tortured you and mentally abused you. it's sine theta is not always y over hypotenuse. You remember this. And in that case, sine theta is y over hypotenuse. But what if I wanted to know that? Sine theta for that angle. Then we're not dealing with y over hypotenuse, we're dealing with x over hypotenuse. In the truest sense of sine, cosine, and tangent, remember SOHCAHTOA. Sine, opposite hypotenuse. Cosine, adjacent hypotenuse. Tangent, opposite over adjacent. Those are the true definitions. What you've just mentioned just lets me know that your teacher didn't really teach you the true definitions. He just taught you a chart. Probably because he was too busy coaching the football team or something. So, yes?
All those multiple choice questions you went through yesterday, have you posted that video or?
The video has already been posted. Yeah, it's already on Google Drive.
Did you go through old tests in previous semesters? Like,
If you go, yeah, take a look. This is the other thing that I would do. It's almost gotten to the point now where I don't have to show up for class at all. I've got so much video. Take a look at the summer and the fall, for last fall and last summer, and you could find the test reviews. And there are some things that are maybe not covered in one semester, not in another it is covered. But for the most part, it is. So you can go back and take a look at and review all of that stuff. I think like the last whole year. So if it says test 1 review, go and take a look at it. I don't think there'll be anything in there because I got to teach the same thing semester after semester. So you can see all sorts of different versions. I will say that this test is probably the most straightforward test I've ever done. You're happy because I get to say this. It's so boring. It's a boring test because I do all the basics. Once the drop deadline is passed and I know I have you, then we can have fun. But until then, and I have to accept the fact that this is your first physics test, we have to stay with the basics. And once we get a few more tools in our toolkit, then we could start doing some more or some different things. But right now, it's a boring test. It's real boring, which means you should be happy. Yes?
Are we need to know any two vision, two unknowns, or 2D motion? Or is it
Could be,
these all-
maybe. I've forgotten what's on the test now.
I thought like, would you solve the same way?
Yeah, it's the same technique.
You just find the.
Yeah. The only difference is that there are different bits of fluff in front of the T's or the X's, different, instead of velocities, they're forces, but the technique is still the same. Solve for one variable, substitute it into the other and solve. Then take that value and chuck it back into the first. And that's it.
It doesn't matter which one you solve for.
No, it doesn't matter at all. So, yes.
there was another multiple choice that was like when you drop something, the initial acceleration is that was 0.
No, we're talking about when I let go and it becomes a free body, it's experiencing a gravity down. What you're thinking about is if the teacher is snarky and said, oh, the moment you let go, the moment you've lost contact with the pen, what's the only force acting on the pen? Gravity. So it's accelerating in that direction. So, all right, any other questions? So for the add vectors, I mean, you could just look at that stuff, and we did that as an example. All right, everybody's starting to head towards the doors. So, very simple exam. I will have this posted by 9 o'clock tonight, and I will see you either at 10, noon, or 2:30 here. The 10 and the noon are at the JAC. So that's it.